This problem, 7.49, is one of my favorite problems. So let's just set it up. Here's what we have. We have a frictionless surface here, nice and flat. We have an incline, looks like this. It has mass m1, an angle of theta here. Angle of theta. Sorry if you can't see that, but that's theta. And on the incline we have there's a frictionless surface between these two. There's another block sitting there, and there's an applied force. Looks like this. Applied force in the x direction here. And the question is, what's the magnitude of the force required such that mass 2 doesn't slip, doesn't move up or down the incline? And this is kind of a tricky problem because what we're looking for is, one, the mass isn't going to jump off the incline. And what we'd like to do in this problem is, like, say, all right, well, let's orient our coordinate system so that it's along the incline like we often do, but it's a little trickier than that, okay? What we want is we want F such that M2 doesn't move up or down the incline. That's what we want in words. The trouble is, though, that it's actually going to be accelerating in the x direction, in this direction. So if we orient our coordinate systems like we might want to for the little mass, we actually run into problems. We actually shouldn't do that because then we have an acceleration in both the x and y directions. All right. So it's kind of a tricky problem. So what I want to do is kind of work through it the way that I would do it. And here's what I want to do. I want to draw a free body diagram on mass 2. Okay. So mass 2, well, it has two forces. It's got m2g acting downward, and it has a normal force acting on it, n, at some angle. An angle is theta there. All right? And so I know Newton's second law tells me that in the x direction, well, I have a component of the normal force, n, and it's the sine of theta, is m ax. And again, just to make it clear, I'm keeping my coordinate systems just like this. The reason why I'm doing that is because the condition that the mass doesn't move up and down the incline is really to say that in the y direction, when I add up the sum of the forces, n cosine theta minus, sorry, that's m2, minus m2g, that is 0. Okay, so that's really what we mean. That there's a significant applied force, so that it's accelerating such that in the x direction it's accelerating such that it doesn't move up and down the incline in the y direction. Okay, and again, be careful. F doesn't act on M2. Right? So I can rearrange these. All right, and here's what we see. If we rearrange x, okay. The requirement is that the acceleration in the x direction on M2, or of M2, has to be, well, n divided by M2 times sine theta. Okay. This expression tells me that n is M2g all over the cosine of theta. And if I combine these two, if I combine, I get that ax, well, I'm going to substitute n in there. Ax is, well, n m2g over cosine theta times, there's a factor of m2 in here, times sine theta. Right? M2 cancels, sine over cosine is tangent, so ax must be g times the tangent of theta. So the acceleration of the block in the x direction must be g tangent of theta. Okay? And so when we look at this now, well, the acceleration of the smaller block in the x direction, because m1 and m2 are connected, is going to be the same as it is for m1. Same as it is for the whole system. So what I'm going to do is I'm going to draw now my system is going to be, well, the whole system is going to be the wedge block system. So if I do a free body diagram on the entire thing, well, in the x direction, the only thing that acts is my applied force. I get some weight force acting downwards, some total normal force from the surface acting upward. But if I do F net in the x direction, goes max, well, there's only one force acting, and that's F. That's going to be the total mass, m1 plus m2, times the acceleration in the x direction, but that's the same acceleration that I found from before. Ax must be g tangent of theta, which means that our applied force has to be m1 plus m2 times g tangent of theta. So again, I like this problem because we have to think through our constraints, our accelerations for the two blocks, and the system of the whole has to be the same. Then we have to be clever about how we do this. So we can do oodles of algebra, but I don't think that this is a tremendous amount of algebra to get to our final, I think, kind of interesting and maybe counterintuitive result. But we have to push with a certain amount of force to get a certain amount of acceleration, and when I do that, the block won't slip.